Hello again, it's Professor Evans. This video is for EET 1214C, which is our Intro to Engineering Technology course at Valencia College. Today we're going to discuss series and parallel DC circuits. Our objectives for this video are that you will be able to apply Ohm's law to a series or parallel circuit. You'll also be able to apply Kirchhoff's laws to a series or parallel circuit. We're going to talk about how to calculate the equivalent resistance for a series or parallel circuit. And then when you do the lab that accompanies this video, you'll be able to measure the total current, resistor voltages, resistor resistance, and total resistance of a series circuit on the bench. So electric circuits can be classified into three basic types. We have series circuits, parallel circuits, and series parallel circuits. And again, we're just going to be talking about circuits today that have a DC source, a direct current source. First, let's talk about the definition of series. A series circuit provides only one path for current between 2 points, and that means that the current is the same through each series resistor. It's really important not to decide whether something is in series based on how it looks. Only one thing matters when we decide what a series circuit is, and that's the path of current. If there was only one path between 2 points, then everything along that path is in series and therefore has the same level of current. So on the screen are several examples of series circuits. In the first example, we have one path from A to B. In the second example, one path from A to B. This example here is where someone might say, well, why aren't these in parallel? When we talk about series and parallel circuits, we have to abandon our idea of parallel when it comes to, say, geometry class and the idea of parallel lines on a plane. Parallel has a different connotation within the DC circuits realm. So when we think about series and parallel circuits, a circuit is in series if there is only one path from point A to point B, regardless of where the path goes or how the path looks or how it's drawn on your paper. So with this one here, there's only one path for current to flow. Therefore, all of these resistors are in series. One path, and again, one path. The biggest mistake I see students make when looking at circuits like this is deciding whether something is in series or parallel based on how it looks and not based on how the current flows. So remember, our definition of series is solely based on current flow and the fact that a series circuit only has one path for current to flow. In a series circuit, we can see that the output of one element becomes the input of the next. So for example, if I have a 9-volt source, current is going to flow through R1, then through R2, then through R3, and back around. Both of these are examples of series circuits, even though in the circuit on the left, all 3 resistors are on the top. The circuit on the right, the 3 resistors are shown around the flow of current. Both of these drawings are fine. Everyone's going to have their preference for how they display resistors, but either one of these is perfectly fine for drawing a circuit that is a series circuit. Now, a defining characteristic of a series circuit is that the current is the same through all elements of the circuit. So once I calculate the total amount of current in either one of these circuits on the screen, I know that that current is the same for resistor 1, resistor 2, and resistor 3. They all have to have the same current if they are in series. Here's how we might wire a series circuit on a breadboard. On the right is our schematic. We have R1 connected to R2, connected to R3, connected to R4, connected to R5. There's our one path. On a breadboard, it looks totally different. Here's R1. On the left side of R1 is how we would connect this to our power supply, and current would begin to flow through R1 through here. Now, because this is a breadboard and every column is a connection point, I've got a wire that allows the current to go from this resistor through to this column where R2 is connected. So current starts here, flows through here like this, and flows through R2 like this. Then current flows through this wire and then into this column so that it can flow through R3 here. Then it flows through this wire to flow through R4, through this wire to flow through R5. So again, the only way that we can define whether something is in series is by looking at the path of current. And in this case, on the right-hand side and on the left-hand side, we have two diagrams that show one path for current to flow. So these are both examples of series circuits. Whenever we have resistors in series, we can add them all together to get what we call a total resistance. It is the sum of each of the individual resistance values. So resistors in series, we can add them up to get a total or equivalent resistance. At any point in a series DC circuit, the current into any given point must equal the current out of that point. Therefore, once again, all resistors in series must have the same current flowing through them. I'm repeating this several times because it's an important relationship that we have to remember about resistors in series. Resistors in series must have the same current flowing through them. Now we're going to learn about a new law called Kirchhoff's voltage law. We've talked about Ohm's law, so now we're adding a new law. Here's Kirchhoff's voltage law. It says that the sum of all the voltage drops around a single closed path in a circuit is equal to the total source voltage in that loop. Here's what that means. Let's say that I have this series circuit. Current is flowing from the battery through the series circuit. And there's going to be a voltage drop. See how the voltage drops are labeled with the polarity? So we can see when current enters, we have a positive sign. When current exits, we have a negative sign, and that's the voltage 1, VR1. Here's the voltage for R2. Here's the voltage drop for R3. Kirchhoff's voltage law, or KVL for short, says that if I add up the voltage drops around this loop, it's going to be equal to the amount of source voltage applied to the loop. Again, this is for a closed loop. This is a closed loop. Current has one path. And if I add up the voltage for R1, the voltage for R2, and the voltage for R3, it should be equal to the source voltage. That's KVL, Kirchhoff's voltage law. Now that we know a little bit more about series circuits and Kirchhoff's voltage law, we're going to do some examples. So we're going to start with example 1A, which is in your lecture notes. Be sure to follow along with me. So we're going to start by determining the total resistance, the total current flowing through each resistor, and the voltage across each resistor in the circuits below. And then we're going to verify that our results are right using that new law we just learned, KVL, or Kirchhoff's voltage law. So here's our circuit. I have a 10-volt source, 6 kilo ohm resistor here, a 4 kilo ohm resistor here, ground. I can see that it's a series circuit with only one path for current to flow. The voltage source is going to have a polarity. Remember, positive, negative. Positive is where current leaves the source and travels around. There's our positive terminal. Current's going to leave the source and flow through R5, through R6, and back around. As current flows, I'm going to get a voltage drop across R5. Here's my polarity, showing the positive where current enters and the negative where current exits. As you are writing your notes, all of the things I'm adding to this diagram, you should also be labeling as well. There's the voltage drop for R6. When current travels through it, we'll get a voltage drop there. And now we're going to start by calculating the total resistance in the circuit. Total resistance in the circuit. I can figure that out because I know it's a series circuit. Therefore, I can add these two resistors together to get a total resistance, R5 plus R6. 6 kilo ohms plus 4 kilo ohms gives me 10 kilo ohms of total resistance. I cannot start to use Ohm's law on a circuit like this until I know the total resistance first. So we're always going to start there. Now that I know the total resistance, I can calculate the total current using Ohm's law. Ohm's law says that V equals IR. Rearrange that. Total current must equal the source voltage divided by total resistance. So in order to figure out the total current, I had to know the total resistance first. I cannot say that the total current is 10 volts divided by 6K. I have to have the total resistance in the circuit before I can apply Ohm's law. That's why we started here. Now that I know the total current, I can continue. So the total current comes out to be 10 volts divided by 10 kilo ohms. Remember, when you type this in your calculator, it's not 10 divided by 10, it's 10 divided by 10,000. And then you're going to get a really small number where you're going to apply your engineering notation to get 1 milliamp. Since this is a series circuit, the current through R5 and R6 is the same as the total current. They all have the same current. So I know the current for R5 and I know the current for R6. We're never going to assume that the resistor, any resistor that we have, has the same current as the total current. Those are always two separate ideas. There will be coincidences where the total current is also the current of a particular resistor, but we don't want to just assume that. It's all based on relationships. Because this is a series circuit with only one path, okay, the total current must be the current through R5 and R6. But we're going to get to circuits where that's not always going to be the case. So I don't want you to assume that. I want you to always verify your results based on a definition, a relationship, or a law. In this case, by definition, R5 and R6 are in series with the source. They all have to have the same current, which is the total current. So I know the total current, 1 milliamp in my picture. So I've updated my picture. And now I'm going to find the voltage drops for R5 and R6. I'm going to use Ohm's law to do that. The voltage for R5 is the current going through R5 times R5. Notice my subscripts. These are very specific. I did not say the voltage for R5 is the total current times R5. It's the current through R5. That's Ohm's law. Now in this case, the total current through R5 just so happens to be the total current in the circuit. It won't always be that way. So I don't want you to get used to writing out, oh, V equals IT times R5. It's not always going to be that way. Always start with your subscript showing the relationship to the element you're looking at. The voltage for R5 is the current through R5 times R5. Then you go and say, well, what is the current through R5? Oh, because this is a series circuit, the current through R5 is total current. And I know I can put 1 milliamp right there. And then I have the value of R5 right there. So that's how I'm going to use Ohm's law. And I'm going to be very specific with the subscripts. So as you're taking your notes, make sure that your notes match mine in terms of how you're writing out each equation with the subscripts and the units. Now that I know the voltage drop across R5, I'm going to label that with 6 volts. Positive, negative. Polarity is important. It matters. Make sure that you have the correct polarity for each resistor. I'm going to apply the same law, Ohm's law, to resistor 6. The voltage for resistor 6 equals the current for resistor 6 times resistor 6. Then you say to yourself, well, how do I know what the current is for resistor 6? And then based off of this relationship, oh, these are in series. Because these are in series, they have to have the same current, which is 1 milliamp. So then I can multiply to get 4 volts. So I have a voltage drop of 6 volts here, a voltage drop of 4 volts there. And I'm going to use KVL to verify my result. So in order to use KVL, here's what we're going to do. You're going to pick a point on the circuit, any point, it doesn't matter. And you're going to go in a clockwise direction. And you're going to add up each voltage that you see. I'm going to start right here. So as I travel along, I get a positive 6 volts. As I keep going along, I get a positive 4 volts. And as I keep going along, I get a negative 10 volts. So my equation becomes positive 6 volts plus 4 volts minus 10 volts equals 0. That is how I set up my KVL equation. You start on one side, you work your way around, you add up every voltage that you see using the polarity you hit first. Polarity you hit first. So that's why it's 6 volts plus 4 volts minus 10 volts equals 0. Then I can see that 6 volts plus 4 volts is equal to 10 volts. I can see that the two voltage drops I had on my resistors equaled the source, which is what KVL said. So KVL said that the sum of the voltage drops around a closed loop is going to equal your source. Another way to say that is that if I add up every voltage that I see along the path using its polarity, if I add up every single voltage along the entire path, it should equal 0. 6 volts plus 4 volts minus 10 volts gets 0. It checks out. Another way I can say this is 6 volts plus 4 volts equals the 10 volts from my source. Either way, algebraically, they are the same. So that is how we use Ohm's law and KVL to analyze a series circuit. Let's do another one. This is example 1b in your notes. We're going to find all the same values. Total resistance, current flowing through each resistor, voltage for each resistor, and then we're going to verify our results using KVL. So now I have 4 resistors, and they are in series because I see that there is only one path. Here's the polarity for my voltage source. I know that the current is going to leave the source and flow that direction through the circuit, creating a voltage drop for every resistor. And my goal is to figure out the current flowing through the circuit and every single one of those voltage drops. That's the goal. Let's start by calculating our total resistance in the circuit. This is a series circuit, so I can add up all 4 resistors. When you add these up, keep in mind, some of these are in ohms, some of these are in kilo ohms. Pay attention to your units and how you're typing these in your calculator. You can type 680 plus 2500 if you want to convert that manually in your head, or make sure that you're doing 680 plus 2.5 times 10 to the third in your calculator. But don't forget, some of these are ohms, some of these are kilo ohms. Then you're going to use that total resistance to calculate the total current for the whole circuit. Again, Ohm's law. Total current is source voltage divided by total resistance. So before we can use Ohm's law, we have to add all these up. Since this is a series circuit, I know that the total current is the current through every single one of these resistors. One path, one current, it's all the same. So there's my total current. Now I can use Ohm's law to calculate the voltage for each resistor. So the voltage for R7 is the current through times its resistance. In this case, we know the current through is total resistance. And once I get my voltage, I'm going to add it to my diagram showing the polarity. There's R9. Here's R8. And here's R10. Again, I'm just applying Ohm's law. I'm saying that the current through each resistor times its resistance will give me its voltage drop. And once I have each voltage drop, I'm adding it to my diagram with a label. And now I'm going to verify my result using KVL. So I'm going to start right here, and I'm going to make a loop around my circuit all the way around. So I'm going to have plus 1.16, plus 4.257, plus 0.23 volts, plus 6.327 volts, minus my 12 volts. And you'll notice here that I have a very small difference. It's not quite 0. It's really, really close to 0. Sometimes that'll happen because we're rounding our numbers as we calculate. So if we were not rounding these answers, we should get almost exactly 0. But because we're rounding the total current and we're rounding the voltage value for each one of these, you may not get exactly 0, but you should get something very, very, very close to 0. So instead of 0, we got negative 0.32. It's very, very close. So our results are verified as long as when you apply KVL, you get something very, very, very small, something very, very, very close to 0. All right, with our second example, we're going to determine the value of our source voltage using KVL. So if you take a look at what we've been given, we have a resistance, another resistance here, a resistance here, a resistance here. We know the current, but what we don't know is how much voltage was coming from the source. What did we start out with? We're going to use KVL to figure this out. So the first thing I'm going to do is write an equation for KVL. I'm going to start right here. I hit a negative sign first. So that's negative Vs plus the voltage for R1 plus the voltage for R2 plus the voltage for R3 plus the voltage for R4. I'm back to where I started, so I set that all equal to 0. That's my KVL equation. Again, you start at one point along your loop, closed loop. You write each voltage that you see with its polarity, and you're making a sum of all those voltages. So I know, if I rearrange this, that the voltage drops across the loop has to equal the source. Has to equal the source if I use some algebra and move that to the other side. Well, what are the voltages for R1, R2, R3, and R4? I don't have them on the diagram, but I have a way to find them using Ohm's law, because I know the current through each resistor, and I know each resistance level. So I'm going to use Ohm's law to find the voltage for R1, R2, R3, and R4. I'm going to plug in the current of 1 milliamp with each resistor value. Now I know VR1, VR2, VR3, VR4. I know if I add them all up, I'll have the source voltage. And that's what I'm going to do. So you end up with a source voltage of 9.5 volts using KVL. Let's move on to example 3, another KVL example. For the circuit below, determine the value of R4. Let's look at what we've been given. I have a DC source where the positive terminal is to my left. Current flows around like this. I know R1's value and I can see the polarity. I can see the polarity of R2 and its value, the polarity of R3 and its value, and I don't know anything about R4. And I also know the total current in the circuit. So we're going to determine the value of R4 using this information we're given. First, let's find the voltage for the resistors we do know. I do know R1, R2, and R3, and I know the current for R1, R2, and R3. Let's find those voltages using Ohm's law. So there's VR1. There's VR2. There's VR3. So I know 3 voltages, and I know the source. So now I can apply KVL to figure out this voltage. So here's my KVL equation. I'm going to start right here. I'm going to go plus the voltage for R1, plus the voltage for R2, plus the voltage for R3, plus the voltage for R4, minus my source voltage has to equal 0. And then I'm going to plug in what I know. I know VR1, I know VR2, I know VR3, I don't know VR4, and I know the source voltage. Using some algebra, you can solve that to get VR4. We know that this voltage plus this voltage plus this voltage plus this voltage has to equal 50. So you can use some algebra to figure out what's the missing voltage. Now that I have the missing voltage, I can find the missing resistance using Ohm's law. Because remember, the question was, figure out the value of R4. What's its resistance? I know the voltage for R4. I know the current for R4. I can use Ohm's law to find resistance for R4. And you get 3.43 kiloohms. So this is another example of how we can use KVL to solve for an unknown value in a series circuit. Now let's talk about resistors in parallel. A parallel circuit has more than one branch or more than one path for current to flow through. Current will divide, go along one or more paths, and then recombine to complete the circuit. So once again, we are not going to depend on how a circuit looks to decide if it's in series or in parallel. We're only going to decide whether 2 or more items are in parallel based on current flow and having multiple paths. So in this circuit, we have a total current that leaves the source, which is right here. And then that current splits. Some will go through R1, some will go through R2, and they'll both recombine right here before returning back to the source. This is a parallel circuit because the current splits, it takes two paths, and it recombines. So that is our definition of parallel, not how it's drawn. Here's another example of a parallel circuit where we can see the current splits and takes four different paths. Path 1, path 2, path 3, path 4. And all of these paths are going to recombine right here. And I'm going to return to the source with the total current that I started with. That's the definition of parallel. Here's some more examples. You're always going to want to take your finger or your pencil and trace the path of current on your paper before you decide whether two things are in series or in parallel. In this case, here's the current. It splits. Some goes down here. Some goes down here. Current recombines. This is a parallel circuit. In this one, the current starts here, splits, some goes to the left, some goes to the right, and recombines. So it's a parallel circuit. Same thing here. Current splits, some goes down, some goes to the right, and it recombines. Same thing here with two paths. This is more tricky. Again, if you're just looking at this, it may not be clear whether they're in series or in parallel. But if we follow the path of current, current flows in. Here's one path, up and around. Here's my second path, straight down. And it recombines right there. So this is a parallel circuit. So one of the most important things you can do is to make sure you understand the definition of series and parallel and make sure that your definition only relies on the flow of current and nothing else. Here's our defining characteristic for resistors in parallel. So we learned that resistors in series have the same current. Resistors in parallel have the same voltage across them. Resistors in parallel have the same voltage across them. And this diagram is two different ways of how we might wire something in parallel. These three resistors are in parallel with each other and the source. This is also a parallel circuit because in both of these circuits, the current splits, takes multiple paths, and then recombines. When resistors are connected in parallel, the total resistance can be found by using this formula. We're going to take each resistance and turn it into a fraction where the resistance is the denominator and the numerator is 1. So 1 over R1 plus 1 over R2 plus 1 over R3. We're going to do this for however many resistors we have that are in parallel. We're going to add them all up and then take the reciprocal. This is how we find the total resistance for parallel resistors. Now let's look at our next example. We have a parallel circuit. Look at the current here. It's going to flow this way, split, and take three paths. So we have a parallel circuit. We're going to calculate the equivalent resistance, and then we're going to use the source to find the current through each resistor. And we're going to look at the total current from the voltage source. Lastly, we're going to use KCL to verify our answers. KCL, let me go back to this one. KCL is Kirchhoff's current law, and it says that the total current going into a node has to equal the total current coming out. So let's say I had 4 amps of current going in, and that 4 amps splits between 1, 2, 3, 4 paths. That means that the 4 paths must have the sum total of what went in. Or in this case, if I had 2 paths, if I had 50 milliamps going into this node, well, some goes this way and some goes that way, but when I add those 2 branches up, I'm going to have the same amount of current that I started out with before it split. That's KCL, Kirchhoff's current law. So let's start with this problem here, where we are going to calculate the equivalent resistance in the circuit. So I'm going to use that formula that I showed you in a previous slide. Little note, when you calculate the equivalent resistance for parallel resistors, your answer should be smaller than your smallest resistance. So it's like a little check to make sure you did it right. Now I can use that total resistance to calculate the total current. I have 3 resistors in parallel. When I combine them to get a total resistance of 23.08 ohms, I can use that to find the total current in the circuit. So I know total current goes this way. I know that total current is 519 milliamps. Some is going to go through R11. Some is going to go through R12. Some is going to go through R13. I know that when I break up this current, if I add up R13's current plus R12's current plus R11's current using KCL, that means I have to add these 3 values up and get what I started with. Now let's calculate the current for each branch. I know the total current is 519 milliamps. I'm going to now find the current for each branch. These 3 resistors are in parallel with each other. They're also in parallel with the source. I know that because as current travels, there's no other node or path or resistors in the way. Current leaves the source and immediately splits. If there's no other element on the path of current, these 3 resistors are in parallel with the source. Parallel elements have the same voltage. If these are in parallel with the source, the voltage of the source is the voltage of each 3 of these resistors. Again, this would change if there was a resistor right here, or right here, or right here. Then these 3 resistors would not all have the source voltage. In this case, all 3 are parallel with each other and the source, so I know their voltages. They all have to have the same voltage. Anything in parallel has to have the same voltage. So I can find the current for R11 by saying voltage divided by R11. And I now know R11 has 240 milliamps of current. I can do the same thing for R12 and R13. And now I know how much current goes through this branch, and this branch, using the fact that these are parallel with each other, as well as the source, and applying Ohm's law. Now I can use KCL to check my work, because remember we said that the current going in has to equal the current coming out. And if I add up 240 plus 120 plus 160, my 3 currents coming out should equal what went in. Now in the previous slide, we calculated the total current as 519 milliamps. When I add these up, I get 520. Again, you're going to get something super, super, super close, but because of rounding error, you aren't always going to get exactly the right number you're looking for. But as long as it is extremely close, you can be sure that your KCL equation verifies your work. All right, here's example 4b. Try this one out on your own using the previous example to guide your way. And then when you're ready, come back and look at the answers. So here's the solution for 4b. Hopefully you were able to figure this one out on your own. Here's our total resistance. Using Ohm's law, we find the total current. There's our total current. And we know it splits 3 ways. I know that these 3 resistors are in parallel with our 10-volt source. So I can use the source and each resistance value to find the current for each branch. And then I'm going to use KCL to check my work. If I add up all 3 branches, do I get what I started out with? Yes, I do. So KCL helps to verify my work. Oh, here's my slide on KCL. We already talked about KCL, but just as a visual representation, like we said, the total current that goes into a node, it splits, it takes several paths. When it recombines, it should equal what you started out with. So here's an example using KCL. We want to determine the current I2 through R2 in the circuit below. We don't know the source voltage. We don't know what it is. but we know we get 100 milliamps of current that goes in this node. Some goes through R1, some goes through R2, some goes through R3. We know how much goes through R1, we know how much goes through R3, we don't know how much goes through R2, and that's the problem, to figure out how much goes through R2. So let's set up a KCL equation. The total current going in has to be equal to the sum of the currents going out. So IT goes in, that's got to be equal to I1 plus I2 plus I3. Fill in what you know. IT is given, I1 is given, I3 is given. Solve for IT. Solve for I2. In our last example, we have Ohm's law for a parallel circuit. We're going to calculate the total resistance for this circuit, the total current produced by the battery, and the total current through each resistor. So I can see that I have a total current here that splits and takes two paths. Here's path 1, here's path 2. They meet together at ground, so I have a parallel circuit with two resistors. So I'm going to start by finding the total resistance of my two resistors in parallel. Then I'm going to use that with Ohm's law to find the total current in the circuit. 100 volts divided by my total resistance gives me my total current. Now I'm going to figure out the current for each resistor. I know that each resistor is in parallel with the source. So in this case, the voltage for R1 is the source because it's in parallel with the source. The voltage for R2 is the source because it's also in parallel. Remember, we have these two paths. So even though the resistor is drawn up here, it's still in parallel with R1 and the source. So we can see R1 flows that way. The current for R2 flows that way. And now we have the total resistance, the total current, and the current through each resistor for this question. Don't forget to use KCL to check your work. I can see that the total current was 2.79 milliamps, and the current for these two branches, if I add them up, I get exactly what I started out with. Now, if you take a look at today's lecture notes, we're going to look at circuit 3A and build it in multisim and verify the values for total current and resistance. If you have multisim, you can follow along with this video, and I'm going to just show you what it looks like to build the circuit from question 3A in multisim. We're going to be using an ammeter to measure current. An ammeter is always going to have to be connected in series with the element you want to measure. We call this breaking the circuit, and the ammeter must be inserted into the circuit between 2 points. What we want to make sure that we do is we direct the entire flow of current through the ammeter and then through the element we want to measure. So it's very important that we remember ammeters have to be connected in series. We use a voltmeter to measure voltage. A voltmeter is connected in parallel to an element like a resistor. That means it's connected to either end of the element. It's going to be in parallel. So ammeters are in series with an element. Voltmeters are in parallel with an element. So here's the circuit from 3A, that 10-volt source with the 6K and the 4K. And here's my ammeter. It's in series. It's in series with the circuit, meaning all the current flows through the ammeter before it begins to flow through R1. The circuit has to be broken and the ammeter has to be placed here. Voltmeters are placed in parallel. Notice how they're connected on either side. How we do this in multisim is something that will be discussed in class and in a future video, but this is just an example of how we would add a voltmeter to measure voltage and an ammeter to measure current. So notice the ammeter is reading 0.998 milliamps, or very, very close to 1 milliamp, which is what we calculated by hand. And the voltages across R5 and R6 are 6 volts and 4 volts, exactly what we calculated by hand. So we can always use multisim to check our work and make sure that what we calculated by hand is correct. Also, I'm going to show you the circuit 4B from today's lecture notes in multisim. We're again going to use the ammeter and the voltmeter in the same way. Ammeters have to be in series, voltmeters have to be in parallel. Here's that circuit from 4B. Here's our total current before it splits and takes these 3 paths. That's that current before it splits and takes those 3 paths. Each ammeter is measuring current from one path. And if I add up 10 milliamps plus 1 milliamp plus 0.2 milliamps, I get exactly 1.21 amps total. That's my current. And if I measure the voltage by connecting a voltmeter in parallel, I can see that the voltage across these resistors is 10 volts, like we said. So the voltmeter is connected to either end. So like I said, the multisim work for the lab that accompanies this video will be in a separate video, and we will go over how to use multisim to take measurements in class. These are just examples. So if you have questions, we will continue to discuss this when you come to class. Any other questions about this video? Here's how you can contact me, and let me know if you need anything.